你在你看我这样。
没有。I'm just going to try and alter the projector. This is the top of the slide. So we've been talking about supersaturation, that's a few lectures really. Just to recap, the supersaturation was proportional, or rate of change of supersaturation. Actually, steady state supersaturation is proportional to the updraft speed, and it's inversely proportional to the first moment of the drop distribution. That's in a liquid only cloud. So this is that quasi-steady supersaturation equation that we derived. And an ice cloud with vertical motion, so just ice, no liquid, it will always be supersaturated with respect to ice, okay, because we've got vertical motion. It can also be supersaturated with respect to liquid, because we don't have any CCM, for example, and the updraft speed is high enough. Because if we do have CCM, normally, which we normally do, that would cause the formation of liquid water, which would bring the supersaturation back down to approximately 0 with respect to water. And that'd be a mixed phase cloud. Mixed phase clouds, they can be long-lived, as long as we've got a threshold updraft speed. And we can also have a mixed phase cloud where we have turbulent conditions, if the turbulence is strong enough. So today I want to talk about the other aspect of rain formation, which is to do with how particles collide and coalesce together if they're liquid, or how they aggregate together if they're ice crystals, or if they're both liquid and ice, how they collect each other. That's known as rhyming. So if we're thinking about the field of cloud microphysics, so I tried to talk you through all of the processes that we usually think about. Think about the first lecture, we talked about how air saturates below the cloud. We've also talked about CCM activation, cloud condensation nuclei, how they grow into water droplets. And that's when we talked about Kelvin's equation. We talked about the curvature effect. Think back to the cloud chamber as well. So we only got a cloud when we had CCM. And we talked about condensation. So we talked about how once droplets form, how they then grow into bigger droplets. So we considered, the laws of diffusion of heat and mass in order to do that, and apply the Maxwellian growth equation. We've not talked about warm rain processes yet. We're going to talk about that today. We've talked about ice nucleation, whether it's heterogeneous ice nucleation at temperatures just below zero, or whether it's homogeneous ice nucleation at temperatures below minus 35 or so, 35 degrees Celsius. And we've talked about vapour deposition. So this is when we applied the Maxwellian growth theory for ice particle shapes, and we used Gauss's law to be able to derive that. And over the last 2 weeks we've been talking about supersaturation theory, or last week even, last 2 lectures. We've been talking about supersaturation theory, and that's allowed us to describe this Bergerac-Finn Dyson process, the Bergerac process, or the Bergerac-Finn Dyson process as it's sometimes called. So we've pretty much covered most of all of these processes. What we've not talked about are processes such as aggregation, how ice crystals collide and stick together; riming, when we've got ice crystals and supercooled droplets, how they stick together; and we've not talked about the warm rain process and collision coalescence, which are related to each other, and how that leads to rainfall. So we've covered most of these processes, but today we're going to cover some more. Another thing that I've not really talked about is secondary ice processes, so I'll mention that today at the end of today's lecture too. So to consider collection processes, collection of particles by other particles, we need to think about how fast particles fall. And so we'll just consider liquid droplets now, just to make things easy. So if we're thinking about small liquid droplets which fall very slow, then the Reynolds number will typically be less than 1. Anyone not familiar with the Reynolds number? Concept of Reynolds numbers in turbulent flow and non-turbulent flow. So for non-turbulent flow, Reynolds number is less than 1. And so for cloud droplets, we can consider the cloud droplets are falling in this regime where Reynolds number is much less than 1, and we can refer to this as Stokes flow. So this is a laminar flow regime. And in those conditions, there's an analytical form of the drag force on a sphere, which goes like this. So this has been derived by Stokes. And if you set the drag force equal to the mass, and you assume that the mass is the volume times density, so volume of the sphere times density, then the result you get is that the terminal velocity as a function of diameter goes as d squared. So for small droplets, there's this d squared relationship between the speed that they fall and the diameter. For a turbulent regime, so when droplets get a bit larger, so we're talking raindrops now, we're at high Reynolds number, and there's no analytical solution to this problem, but we can apply usual technique of calculating the projected area of the particle normal to the flow and setting a drag coefficient. So we've got projected area times rho, which is density of air, times u squared over 2, and the drag coefficient is 0.5. Have you seen that formulation before? Has anyone not seen that? So I think you are familiar with that. Okay. So again, set the drag force equals to the weight if it's at terminal velocity. And so for large particles, we find that the fall speed goes as e to the 0.5. So we've got these two regimes where we have, when I think about a graph, the particle's diameter against its terminal velocity in the air. So for small particles, it goes as d squared, Stokes' flow, and for large particles, goes as the square root of d approximately. So there's some intermediate regime where neither is true, so the transition between the two. Okay, so we can think about that kind of curve. So we generally assume that particles fall at their terminal velocity, and now we need to think about, if we're in a cloud, let's think about in a cloud, droplets are more or less the same size, but there's some region of that cloud that leads to conditions where a few droplets become larger than the rest of the droplets. So whether that's a fluctuation, a turbulent fluctuation leading to an increase in supersaturation in that region, which allows droplets to grow larger than others, or some evaporation process which evaporates some droplets and not others, we don't know, but we're just assuming that a few droplets grow to slightly larger sizes than others. Okay, and if that's the case, we can think about this kind of setup. So we've got the large droplet which has grown larger than the rest of the particles, and we've got smaller droplets here. Now, what I'm considering here is the fact that the larger droplet will fall faster than the rest of the other droplets. So if you've got small droplets in the cloud and a larger droplet above the cloud, this larger droplet will fall through the cloud of small droplets. Okay? And due to the flow field around the larger droplet, smaller droplets that are within the projected area of the larger droplet may be deflected away and not collide and coalesce. But at some distance y away from the central point, then particles will make a glancing collision and collide. Okay, that distance y, or the ratio of the area of the disk of radius y to the area of the disk that's radius r1 plus r2, where r2 is the radius of the small drop, is known as the collision efficiency. That's the collision efficiency. So we use this concept called the collision efficiency. So I'll try to explain a little bit more about what I mean by collision efficiency. I'm just going to go to the visualizer now. So we had, for small droplets, first of all, for small droplets we had the terminal velocity is proportional to d squared. So this is small droplets. This is d squared. And for large droplets, the terminal velocity proportional to d to the 0.5. Now, so I said we talk about some droplets in a cloud growing to sizes that are slightly larger than the rest of the cloud. Okay, so we've not defined what that is yet. It could be some increase in supersaturation or decrease in supersaturation, which just means that some droplets grow larger than others. And so, if I've got two droplets, a large drop and a small drop, the large droplet first of all will fall faster than the small drop, and if we consider these two droplets in the reference frame of the small drop, so we're constantly watching this small drop, then I can consider the volume swept out by this large drop in the reference frame of the small drop. So this is U at size d, so this is diameter d, and this is U at size little d, this is diameter little d. So the volume swept out per second, okay? Let's think about what that is. So I'm going to define this quantity. Volume of air swept out per second in the frame of reference of little drop. So my camera follows the little drop, and if I do that, this big drop will come past at some point. So that volume of air, which we'll call V, is going to be pi, and this is for a glancing collision too, so pi times d plus d squared. So right now I'm saying that if a small drop contacts the edge of this big drop, it will coalesce with it. So the volume swept out for droplets that will collide with this big drop is just the area of a disk that's diameter d plus little d, which is pi times d plus d squared over 4, and then multiplied by the difference in the two terminal velocities. If you think this is an area, this has units of meters squared, and we've got meters per second here, so this is meters cubed swept out per second. Meters cubed per second. So this droplet and this droplet sweep out an area of sweep out an area of this volume every second. Okay, so it's meters cubed per second. That's the volume swept out per second. And now, if I think about the concentration, the number concentration, of cloud droplets that are of diameter little d, I'll call that n. And if I multiply little n by big V, so if I multiply n by V, then that has units, because number concentration has units of number per meter cubed, it's the number of particles per meter cubed, then the product of V times n has units of number per second. Let's think about what that means. Number of cloud drops, size B, per meter cubed of air, volume of air swept out per second by this drop pair. So the product of V and n is the number of collisions per second. That would be the number of collisions between the big drop and the small drop per second. So that's number of collisions per second. Now, as I said on the previous slide, we also have this thing called the collision efficiency. So collision efficiency takes into account that not all droplets that are a distance d over 2 away from the centre line will collide and coalesce. Okay, so the actual number of collisions will be V times n times the collision efficiency, E. That quantity I defined on the previous slide. So actual number of collisions per second is V times n times E, which is a two-dimensional function which depends on the size of the big drop and the size of the little drop. But for the purpose of this course, we're going to assume that E is equal to 1. So it doesn't actually matter for the purpose of this course. But you do need to be aware that there is this quantity which defines the efficiency by which these two droplets collide. Okay, so if we look at V, if we look at now the volume, so I should call this volume of air, this quantity here, let's call it volume of air, otherwise it gets confusing. This is volume of air swept out, and that's volume of air swept out. Now, if I know the number of collisions per second between droplets of size d, then if I multiply that by the volume of a drop size d, then that gives me how much volume would be added to the big drop per second. You get that? Explain what I mean. So the rate of change of the volume of the big drop is just equal to the volume of the air swept out multiplied by the number of little drops multiplied by the volume of the little drops. So each little drop has a volume Vd, and Vd is pi over 6 times d cubed. That's the volume of a sphere, its radius d. So then, volume of the air swept out times nd. There should be a collision efficiency there too. Strictly, but we're going to assume that's 1. This thing here, Va times nd, that's number of collisions per second, multiplied by the volume that is added to the big particle for every collision, and we've got volume added to the big particle per second. Does that make sense? Anyone confused about that? Okay, so fairly straightforward looking differential equation. And if you want to see this equation broken down into its component parts, look at equation 4.8 in the notes. So it gives you a bit more detail on the derivation. So it's in the PDF of notes for this lecture. So if you go back to my web page, this week on my web page, same as every week, there's a PDF as well as the slides, and there's a bit more detail in the PDF which goes through the derivation. So that's the rate of change of the volume of the big drop, and we can make a change of variable to change this volume into a diameter, because we know volume is pi over 6 times d cubed, and by doing that we can get a differential equation that tells me what the rate of change of the drop's diameter is, the big drop's diameter. I'm not going to do that, I'm just going to write down what that's equal to. So we've got the collision efficiency, which we assume is 1. We've got the mixing ratio of liquid water, and we've got the fall speed of the big drop, which I'm assuming is a power law, a d to the b, where b is 0.5, so that's square root term, and we divide by 2 times the density of liquid water. So in this equation, just define some terms. E is the collision efficiency, we assume that's 1. WL in this case is the liquid water content of the cloud. Which has units of kilograms per metre cubed, kilograms of water for every metre cubed. Rho W, that's the density of water. So that's 1,000 kilograms per metre cubed. A turns out to be about 1.47 times 10 to the 2. This is A is derived by balancing the drag force with the weight force. So if you calculate what A is in that power law in the previous slide, you'll find it's approximately equal to this. And B is 0.5, because the fall speed of the big drops goes as the square root. So this differential equation describes the diameter growth rate of a droplet that finds itself bigger than the other droplets in the clouds. It's the diameter growth rate due to collisions between droplets and eventual coalescence, meaning that when droplets come together. Okay? And the solution looks something like this. So you can all solve this differential equation. So I'll just write down the solution. It's diameter as a function of time, and we've got E WL A into 1 minus B divided by 2 rho W plus D naught. D naught's the initial diameter, 1 minus B, 1 over 1 minus B. So a fairly complicated looking solution. So if you were to differentiate that and substitute it in here, you find that they're both equal. So this equation describes how we start with a droplet that's bigger than the surrounding cloud, and its initial diameter is d naught. Then this equation describes how its diameter changes with time for a constant liquid water content. Okay? So let's have a think about what that means now. So you remember a few lectures ago I showed you that growth of droplets from water vapour leads to a narrowing of the distribution, and we said that couldn't on its own describe how precipitation forms. So what we did was we looked at, against time, we looked at starting with two droplets that were separated in diameter, and we found that as time goes on, these two droplets become closer together in diameter space, and we don't see that. So observations don't show that. When we looked at it for ice crystals, we did a similar thing. Ice crystals, I think I was looking at growth along either one of the crystallographic axes, let's say it was the A-axis, and we found that for ice crystals, if we start with two particles that are separated in length, then that distance remains constant with time. So that can kind of explain precipitation, but it doesn't explain the fastest precipitation process that we see. Now what I want to do is do the same for collection processes. So I'll apply that equation that I've just derived, well I didn't derive it, just written down the solution of. We'll apply this equation now. So we're going to draw a similar diagram. This is time. We're going to start with d naught for the first droplet. We'll start with d naught for the second droplet. So the initial diameters are separated. And so if you go back to here, B here is 0.5. So this is 1 divided by 1 minus 0.5, which is 2. So this exponent here is 2. And this one here is 0.5. 1 minus 0.5 is 0.5. So I can write this down. If I take the square root of both sides, I can write this down as dt to the 0.5 equals, let's call this a constant A. And by the way, there should be a T there, which I've missed off. That's time times T. and then plus d naught to the 0.5. Okay, so that's the basic form of the solution here. So I'll go back to my graph. So I'm going to start with, so I've got d to the 0.5 equals, I'm going to consider growth at some time t here. So a times t plus d naught to the 0.5. So for the first droplet, it doesn't matter what the units are, we're just looking at the form of these equations. We'll pick d naught is equal to 9, and we'll pick that the product of a times t is equal to 1. So if we do that, we find, so d naught to the 0.5 is 3, plus 1 is 4, and that equals the square root, so d must equal 16 in that case. And for the second drop we'll do the same, but we'll pick d naught equals 16, product of a times t is still a constant, it's still 1, and in that case we've got the square root of 16, which is 4, plus 1 is 5, and that equals the square root, so d in that case must be 25. So the initial change in diameter between these two drops is 16 minus 9, so that's 7, delta d naught, and the final change, delta d, is equal to 25 minus 16, which is 9. So this actually predicts a broadening of the distribution, slight broadening. Okay, so we've got a few different scenarios. We've got growth from the vapour, can't describe precipitation. It predicts that all the cloud will fall out at once. It predicts that it takes about 3 days to form precipitation size drops, which is longer than the lifetime of most clouds. We've got the ice process, cold rain process, which doesn't predict a broadening of the drop size distribution and can lead to snow in a reasonable time period. I think maybe 10 minutes from our example, or 20 minutes, something like that. Actually, it's a bit longer, 20 minutes. This case predicts a broadening of the drop size distribution, which is consistent with observations. And if you substitute reasonable numbers and calculate the time it takes to get a droplet of, say, 2 or 3 millimetres in size, a typical drizzle size drop, then the time taken for that, I'm not going to do that, it's quite straightforward, but the time taken is about 10 minutes. So again, broadening, the fact that this theory predicts a broadening of the drop size distribution, and the fact that we can get rain within about 10 minutes leads us to say that this process can be responsible for precipitation. Okay. Let's go back now. So, so there is a slight subtlety in that observations show that we have small droplets as well as large droplets, and if we're treating the precipitation process using this collision coalescence theory that I've just talked about, then collision coalescence theory predicts that the cloud would grow to larger droplet sizes and would broaden. So where do the small droplets come from? But it turns out, and we're not really going to go into this in too much detail, it turns out that during the collision coalescence of some droplets, if the interaction is strong enough, if there's enough kinetic energy, then that can lead to collision-induced breakup. Okay, so similar to this sort of scenario, big droplet, small droplet. If it's high collision kinetic energy, then that can lead to breakup with a big droplet and some small droplets. That's for some collisions, not all collisions. And this happens via different breakup mechanisms. So they're referred to as bag breakup, disc breakup, or sheet breakup, or also filament breakup. Bag breakup is when you have a collision and then the droplet develops some instability, stretches out, and because it's falling through the air inflates the droplet like a bag before it disintegrates. Disc is where it stretches out and just disintegrates straight away without inflating. Filament is where you develop the instability and then the droplet stretches out like a long, what do you call it? Like a long sausage, and just breaks up into several droplets. And if you want to see some examples, there's a YouTube video link there. You can see some examples of raindrop collisions filmed with a high-speed video, and you can see them breaking up. But you don't need that. You don't need to look at that for the exam or anything. So snowflakes. So that's how liquid droplets collide and coalesce. For snowflakes, so I mentioned the pristine habits are quite rare, and 90% of the time snowflakes are actually aggregates. So that gives us a hint on what processes are important for the growth to these sizes. And we can treat the growth of snowflakes in much the same way. So we can apply the same theory. So I'm not going to go through it again, but I'll just show you some examples of why we can treat it the same way. So two ice crystals, one falling faster than the other, and we can develop the same theory by talking about the volume swept out per second by both of these ice crystals in the frame of reference of one of the ice crystals. So it's the same kind of thing, same kind of idea. Instead of the collision efficiency, the coalescence efficiency, we talk about the aggregation efficiency, but by and large, it's much the same thing. So there's a little slide there about how ice can stick to ice. I'm not going to go through that. I want to come back to this cloud that we've been talking about. Okay, so now we've covered pretty much all of the processes in this cloud. So I've talked about CCN activation, condensation, collision and coalescence. I've talked about breakup. So when two droplets come together and you get this breakup. Talked about ice nucleation, vapor deposition, homogeneous freezing, heterogeneous freezing, and the Bergeron-Findyson process. And we've talked about aggregation too. Rhyming's treated in much the same way. The thing I've not talked about are these mechanisms called secondary ice processes. Okay, so this is a fairly active area of research that people don't know a huge amount about, and we're trying to understand more about it because it seems like it might be important for things like weather forecasts or climate forecasts. So one such mechanism that we do know a bit about, so first of all, what is secondary ice? So secondary ice is where we have some ice crystals that form from heterogeneous or homogeneous ice nucleation. So we call that the primary ice formation mechanism. So we've got some ice crystals in the cloud, and secondary ice is how we can get some more ice, but not from nucleation. So how does that happen? Well, one such mechanism that we know a bit about is called the Rime splinter mechanism. And I'll try to explain it here. It happens during rhyming, so when ice crystals accrete liquid droplets. And so if we have an ice crystal which forms from, say, primary ice nucleation, and we have a droplet which approaches it, and they need to be greater than 25 microns. And this droplet it comes in contact with the ice and sticks, and it starts to freeze. And the droplet freezes from the outside in. Okay, and that's just because it's easier for the outside of the droplet to radiate the heat away, the latent heat away. So when it starts to freeze, the heat gets transferred away from the droplet more quickly around the droplet shell. And so an ice shell forms first, and then the inside of the drop starts to freeze. And because ice is less dense than water, when the inside of the drop starts to freeze, the volume starts to increase. Actually, the pressure starts to build up. And it can build up to such a point where the ice shell can crack. And when it cracks, it can eject all these small ice splinters. Okay? Make sense? Okay, so that's known as the Rhine splinter mechanism. And you see, this sort of dates back to the 70s. So this is our understanding from the 70s, and it's not really progressed much since then because it's so difficult to observe this in the lab. There's actually what we refer to as a Goldilocks effect. Familiar with Goldilocks and the Three Bears? So one, what do you think of that? You know, one bear's porridge was too hot, one bear's porridge was too cold, the other bear's was just right. Okay, so it's the one in the middle that's just right. Okay. So by Goldilocks we mean if you look at the number of secondary ice particles that are ejected and when that ice shell cracks, as a function of temperature, it looks something like this. There's a maximum at -5, and it drops off either side, down to 0 by -10 and 0 at -2. And we can explain this Goldilocks effect. You see, the data look a bit dodgy, because it dates back to the 1970s or so. There's no error bar on this plot, but this is currently our best understanding of the process. No one's actually gone away and measured this process again in the lab with more accurate equipment. Okay, so there's no real error bar, someone's just drawn a line through this data, and that's our best understanding at the moment. So let's think about it. At the lower temperatures, we think what happens is that when the ice shell forms around the droplet, the freezing droplet, at lower temperatures the ice shell is really strong and it's resistant to cracking under the internal pressure as the inside of the drop freezes. So that's why we don't see ice multiplication at the higher temperatures, lower temperatures. And at the higher temperatures, what we think happens is when the droplet moves towards the ice crystal and contacts the ice crystal, it spreads out before it can freeze. That's because the rate at which it freezes at the higher temperature is much slower, so it gives it time to spread out onto the surface of the ice crystal, which means it's less likely to develop an ice shell. There's less volume for the pressure to build up and crack the ice. So we've got this Goldilocks effect of how two processes compete. Does that make sense? Okay, so that's just a fairly interesting way in which ice can be multiplied in a cloud. Why am I talking about it? Why is it important? Okay, so so we think it's important for things like precipitation, and I've just done a little basic model simulation here to show you why it's important. So the basic model calculation, I've called it a simple cloud model calculation, and it's a 1D column, so it's just a one-dimensional column, a vertical column in the atmosphere. So the column starts at the ground, goes all the way up, and we initialise a cloud in that column at time 0, which is given by these black contours here, and the cloud base has a temperature of 12 degrees Celsius, and the cloud top has a temperature of around about -20. So it's a fairly typical cloud. And we just see what happens as a function of time in minutes on the x-axis there. And I've done 2 simulations in both cases. I've done a simulation where we have this rime splinter mechanism switched on. So this mechanism where we can get ice. And I've done a simulation where we have it switched off in the model, so we don't consider secondary ice. And I've done several simulations like this. The difference in the simulations is that they have a different number of primary ice nuclei. So IMPs here, set to some very small number in this case. So when we have low numbers of IMPs, 10 to the minus 1, 2, 3, 10 to the minus 4 per litre, that's a very small number of primary ice. Then we can look at, and what I've plotted, it's a contour plot of the difference in precipitation from when we have the rime splinter mechanism on to when we have it switched off. Does that make sense? So if you look at the case where we've got low numbers, we don't see a difference for when we have rime splinter switched on to when we have it switched off. So there's no difference there. And then we start to increase the number of IMPs, 10 to the minus 3, 10 to the minus 2, 10 to the minus 1, all the way up to 10 per litre. And so what we can see is when we increase the number of primary ice nuclei, we can see that, and we have secondary ice switched on, so we have the rime splinter mechanism switched on, we get more precipitation. So it seems that the more, although we have more ice in both cases, more primary ice, because of the secondary ice, we get more precipitation. It leads to a more efficient precipitation process. That's why we think it's important. And at the moment, these processes aren't generally included in weather forecast models. So these secondary ice, because they're so uncertain, because there's no error bars on our laboratory plots, they're not included. But we do know it does take place. So we have measurements in the real atmosphere showing that in certain situations we do see the we see the rime splinter mechanism of secondary ice. So we know it takes place, we know it's important. At the moment we're at the stage of trying to put it into weather forecast models. Okay, so just some main points there. The main points, there's quite a lot of information there, but the main points to take away from this are it's actually gravitational settling that can explain why drops and snowflakes can collide and coalesce. And why is it gravitational settling? Well, the bigger droplets fall faster than the smaller droplets due to gravity and air resistance. Drops and snowflakes can also break up when they get large. That leads to these exponential distributions that we see in the atmosphere. And the collection processes, so we'll talk about droplets collecting other droplets and snowflakes collecting other ice crystals, aggregation, they can lead to precipitation much faster than growth from the vapour. It's not really surprising. And when we talk about rain, we can talk about the warm rain process. So this is generally referred to as when we have collision coalescence between drops. And we can talk about the cold rain processes. So when we talk about cold rain, we're talking about mixed phase clouds, ice growing faster than drops due to the Berger and Dyson process, this taking place, and also when they aggregate too. So it's another collection process. So that's the end of the lecture, but I just wanted to show you a couple more slides to see what you think about these. This is something that I looked at about 10 years ago. I was involved in some research and I'd like to show you the research that we did, which was it's on ice crystals. They are ice crystals in a cloud. So these are the observations, and they're observations from a LiDAR. It's a laser that points vertically in the atmosphere. And you can see with this LiDAR the extinction coefficient. Extinction is how much of the laser radiation is attenuated when you shine it up into the atmosphere against height. And we can see a dust layer below the cloud, and we can see a cloud layer here, about 5 kilometres above the surface in this case. But if we look at the temperatures, you can see temperatures are very low, even at the surface, minus 60 or so. So where do you think these clouds are? Whereabouts would you say these clouds were? Anyone know? Anyone want to guess?
It's below 80 degrees at surface.
Oh, yeah, minus 80. Yeah. Where could these clouds be? The actual temperature of the clouds at 5 kilometres is more like minus 70, I guess. Where do you think?
Antarctica.
Say again? Antarctica. Yes, okay. So these are the actual observations. So this is height. This is the same data, but plotted as a function of time, and the colour is the backscatter coefficient, how much laser radiation is backscattered back to the surface. Okay, you see that? You see the clouds? So these are ice crystals aggregating together and starting to fall towards the surface, but not quite reaching the surface. They're evaporating before they reach the surface. Can you see that? So if I give you a clue, you see this? Sol. Does that give you a clue as to where these clouds are? Thinking maybe the physicists or astronomers. Now these clouds are on Mars. So these are Martian clouds. These are water ice clouds on Mars. Okay, so these were observed during the Phoenix mission.